As said, my name is Lucy Spouncer. I'm at the University of Edinburgh. I work specifically in the Algebra, Geometry and Quantum Field Centre for research at Edinburgh. And today I would like to reframe and apply some of the pillars of thought of this Platonic Space Symposium, both from the perspective of the proposed research framework and also the philosophical framework, by making a comparison to an interpretive framework of mathematics by researcher Irida Altman at ETH Zurich. So firstly, I would like to thank Irida Altman for her help with getting through for understanding her thesis and her research. I'd also like to thank Joel Dietz and Mariana Valdataro for supporting me through preparing this talk, and the SEMF community, the Society for Fundamental and Multidisciplinary Research, for their support, and of course Michael Levin and Hanan Hassan for organising this symposium, and all of you for being here to watch this talk today. I would like to first make a disclaimer that Irida Altman, in her research that I'm using today, makes no claims about agency or ingression, or indeed any claims about the ontology of mathematics. So any discussion on these topics are comparisons that I personally am drawing with the hope of extending the proposed research framework of Levin productively to mathematics. So, yeah, let's begin. So first I would like to share with you an anecdote from when I was an undergrad in my mathematics degree. And for years and years throughout school and the first few years of university mathematics, you learn about lots of different mathematical objects, including, modular arithmetic, like subtracting 12 from when a number gets too big when you're counting on a clock, times tables, then more sophisticated coordinate plane and geometry, vector spaces, matrices and polynomials. And I want to share with you, I was one moment where I was sat in the library reading through my third or second year algebra notes, and I came across this chapter on modules, and I was given this name for the ground in between all of these concepts and many more that I've not written on the screen. And suddenly I could just perceive this vastness of the landscape that I'd been exploring for years and that I hadn't even known was all there. And knowing about the abstraction of modules, it didn't help me understand the peaks and the terrain in any better way. It just gave me a more direct way to go between the peaks. And on its own, abstraction in the traditional sense does not give you any of the richness of the mathematical landscape. So yeah, I was just sat there in the library and I couldn't help but cry in awe at this vastness and beauty and the freedom to walk this landscape. So Alexei Tolkinsky, I take your warning to be cautious of such feelings of awe, leading us towards agential explanations. So my intention today is to remain firmly grounded in the physical world for the following comparison. Okay, so I'd like to first introduce the relevant aspects of the philosophical and research frameworks that have come from this Platonic Space Symposium so far. Firstly, we're working with mathematical and computational agents or patterns as causal agents. So an example of evolution exploiting mathematical truths as affordances is of cicadas, with using the primeness of their life cycle, so 13 years or 17 years, to avoid predators more successfully. The second point would be that there is a structured Platonic space with agency gradients, specifically that patterns ingress from this structured non-physical space of agential patterns to a physical substrate. And this Platonic space contains not just passive mathematical truths, but agential patterns, including kinds of minds, and physical embodiments serve as pointers or interfaces to this space. The third point generalizes the symmetry that Michael Levin and collaborators have been working in between neuroscience and developmental biology. So there's non-physical patterns as behavioral pivots generalizes the idea of cognitive patterns as evolutionary pivots. So instead of just considering the mind-brain relationship mirroring the patterns, the relationship between patterns and morphological outcomes, perhaps it also mirrors a relationship between mathematics and physics. In terms of the research framework, I'll be focusing mainly on the affordances of both biology and mathematics, or the properties of both that make it amenable to this scaling for behavior to coordinate across many different organizational levels, and this idea of homeostasis or set points in intelligent systems. I'm going to practice, I'm going to perhaps comment on observing patterns without selection pressure, which is a nod to the research in synthetic morphology of taking, say, the tracheal cells of frogs out of their environment in the body of a frog and putting it in some different contexts and seeing what behavior emerges. And finally, I will be using very simple systems as probes for this platonic space, or to test agency, and whilst maintaining or avoiding some reductionist perspective, so that we're able to remain open to capabilities of simple systems that we might not have expected previously. I'm going to be using a couple of definitions of agency. One is achieving the same goal by different means, and another introduced by Benjamin Lyons in his talk Agency from the Bottom Up, which I would recommend if you haven't already watched it, of agency as choice making, so making trade-offs as necessitated by logical consistency. And this was an argument that scarcity in economics was related to logical consistency in mathematics, because the way that we get abundance in mathematics is from contradiction or logical inconsistency. If we assume the sky is blue and the sky is also not blue, then we can kind of derive any mathematical truth that we would like. Yeah, so that was the argument there. So for me, I see a very productive philosophical tension here. This anti-reductionism, so yeah, life isn't just chemistry, and anti-Mysterianism. We shouldn't just accept emergence. So simple systems can do interesting things, but we better have an explanation for why. And I think a framework that navigates this tension very well is an interpretive framework that's currently it will be out in a few months, entitled Textuality in Mathematics. It's a hermeneutics, an interpretive framework for mathematics, by Irida Altman at ETH Zurich. So let's all agree what mathematics is. In this presentation, mathematics is a collection of practices around manipulating societally shaped systems of things that are like languages, quasi-languages. And without further ado, I would like to introduce to you the relevant aspects of Altman's interpretive framework for mathematics. Okay, so first, I would like to reframe ingression and challenge this idea of the non-physical space. I claim that it's not necessary in order to practice the framework proposed by Levin and collaborators. So, from my perspective, any way that I can understand, manipulate, observe, reference, communicate, or whatever else, the number 13, it's all physical. And that's the standpoint I'm taking today. So I want you all to ingress from a non-physical perspective to a physical one. And by that I mean I'm going to translate some of the existing practical and philosophical ideas to an ontologically agnostic and very physical framework. I think an illustrative concept or idea is in the following phrase that you want to think about throughout the talk, is that mathematical symbols in literature do not represent something. They are just marks on a page. They are presentations. They do not represent, they present. And this takes away this like master object, this abstraction, this pattern in this non-physical space that ingresses into all the physical substrates. So here, 13, the life cycle of the number of years of the life cycle of a cicada, the number of protons in an atom of aluminium, the number of flowers and the number of petals on this flower. It doesn't require us to have this master object. In fact, to understand and work with productively the research implications of ingression, we actually are able to put everything on the same physical level. And to 13 as a typed set of digits, or as a response in our brains, some electrical signals being fired around, those are no less physical than the life cycle of a cicada, or the number of protons in an aluminium atom. Okay, so in order to talk about multi-scale competencies and understand this better, I want to look at properties of the substrates of biology and mathematical language. So here's some units of biology and mathematics. So units of biology on the left here we have molecular networks, single-celled organisms, clusters of cells forming embryos. We have kind of parts of organs, whole organs, organisms, and I could even go further and say, collections of different organisms or even whole ecosystems of different species. And on the right-hand side here we have units of mathematical language, individual symbols and characters, marks on a page. We have words from natural language, we have equations, we have logical statements, we have graphs, diagrams, we even have whole collections of all of these assembled into propositions, statements, theorems, definitions, proofs. And so what are the similarities here? Well, we have iterability being a key one of the units of our biological and mathematical substrates, and scale flexibility. I also want to ask that the units of mathematical language and the presentations have ontological agnosticism. So without an interpreter, these physical presentations have no meaning. So when looking at mathematical language, what distinguishes it from other languages? What helps us recognize scaling and individual agents in both mathematics and biology? I would say a very foundational aspect of mathematics that you quickly learn to get your head around is demarcation of boundary. We need a thing, we need to know the boundary of that thing and a way to probe it or move across that boundary. So many, many examples in just this short bit of text. Here we have the definition of the difference of two sets. First, we've separated the mathematical environment as a definition, so this whole paragraph is separate from the rest of the text. We then have bold fonts and italics to separate, okay, well, the name that we're giving this definition or the new term we're introducing. We have italics for symbols, mathematical symbols. We have new lines and centering, our alignment. We have quite large line spacing to, again, separate the boundary between what is that equation and what is not that equation. We have bracketing to denote elements that are inside the set and outside the set. We even have diagram shading down in the bottom here to denote which elements we're considering in this definition. The ones that are inside the circle representing labeled A and that are not in the circle with the label B. So similarly, we might think of traditional views on biology we transition from physics to biology when the cell membrane starts to appear. We have ways to cross this cell membrane or to understand movement across the cell membrane, maybe through concentration gradients or other bioelectric signals, these kind of things. Of course, the modern viewpoint is that it's much more flexible than that, but just an idea there. So once we have these boundaries, we have individual units, and these very clear-cut boundaries allow us to scale, to nest the individual presentations into collections of presentations which form new presentations. For example, we have the labels denoting our sets A and B, we have an expression A minus B, and then we have that whole expression A minus B put into an equation, which is again another unit of mathematics, and you can see how this happens very, very quickly. Mathematics is very efficient in this way at building up the scale very quickly. So for a hermeneutics, what we need is a thing, its boundary, and a way to cross that boundary. So we need a static component, which are our units that we've already talked about, and we need a dynamic component. So what is the dynamic component? Where are we going to find our movement in this theory, this framework? So the units of movement are called directions of interpretation. And we see in the same example, we move from the phrase, the difference of two sets A and B, to the symbolic expression A minus B via the word denoted. And this is an identity direction. Denoted usually means, okay, this is just another way to write this concept. And so this is one particular direction of interpretation. And I claim that's how we're moving between the life cycle of a cicada to some digital typed number 13 in a spreadsheet recording that life cycle. And again, perhaps typing in 5 plus 8 in the calculator, writing down answer with a pencil on a piece of paper, number 13, or counting the number of petals in a flower. Each one of these movements is an interpretation, but it's not on its own. We can scale up these individual presentations, these individual physical instances, to whole systems. So I could take the system of animals in general and their life cycles. So I could take any particular animal that I can measure the life cycle of, and I could convert that or translate that into a number. So each of these interpretations is part of a translation. So translations are kind of group collections of aligned interpretations. More formally, some type of equivalence relation between presentations or presentation systems. Here we have the individual interpretation of the phrase n by m matrix to this two-dimensional diagram that shows us the elements of our matrix indexed by their position. And so we have different types, different examples of translation. We have moving from general to specific and back again. So when we say difference of two sets, we're taking a very general view. We can specify the sets A and B and perform some kind of computation. We can also translate from real life scenarios to word problems. Say a ball dropped from rest at the top of a 45-meter tall building. How long does it take to reach the ground? And we can formulate that in turn in a very formal way. So that's kind of, I guess, translating or moving in the logical direction, or the formal direction, sorry. Here with each of the different variables and the equation. We can also move between geometry and linear algebra. So we have here the depiction of two lines intersecting and translating that to a system of equations, or an equation involving matrices and vectors. So what I think is really important to me, so this is how this links to my personal kind of interest or investment in this symposium, is that the translation from real life scenarios to word problems to formal presentations, and then kind of towards even further degrees of abstraction, is the kind of movement or kind of work that I do day to day, moving between mathematical physics and pure mathematics. In fact, communication between these two different areas of maths is challenging. We have very different practices and conventions and ways of communicating ideas. So I would like to be able to take biological theories and apply them to understand mathematical practices better, to inform this movement between physics and pure mathematics. Okay, so properties of these translations is that, well, when you make a translation, ultimately you're losing some things and gaining some other things. And so every system of presentations, for example, this system of words, matrix, vector, matrix multiplication, etc. This is a system of presentations, and it has its own affordances. Mainly, okay, I can read these out very, very simply. I can say n by m matrix. To describe this two-dimensional, depiction here of brackets and the individual indexed elements of the array, it's a bit more cumbersome. The words can be embedded into kind of just full sentences, flowing text. They're quick and simple to type. And I can pluralize them. I can do any grammatical manipulations, as in natural language, but these affordances can be phrased both as enabling or constraining. So the fact that I can embed it in line in a flowing text means that it's actually it's predisposed to work better in those contexts. It would be very difficult to take it out of those contexts and just put it randomly separated from a sentence on a page. It doesn't hold much meaning that way. It can't be interpreted very well in those contexts. And similarly, the fact that I can't put these two-dimensional matrices and vectors, these diagrams into a sentence is actually a very important strength, because it means I can move them around each other much more obviously in 2 dimensions, and also I can see their internal elements, which means I might be able to produce new presentations which hold information about the elements of the vector and of this matrix that I see already on the slide. So, like everything else, translation gaps depend on the context and the interpretational conventions of the community and individual. But here are some that apply in a lot of different contexts to the average observer or interpreter. Okay, so I want to link it back now to one of the definitions of agency as choice making, that we saw at the beginning, by saying that, okay, well, translations exhibit varying degrees of complementarity in affordances of their presentation systems. So when you have a translation, you have a kind of comparison of the affordances of one presentation system with the affordances of the other. And those affordances, those differences in affordances, give rise to interpretations that have varying degrees of logical consistency with one another. And so when we know that from this definition by Benjamin Lyons, that when we have some degree of logical inconsistency, then a choice must be made. So that's how I start to kind of tie the story together. So how does this frame the spectrum of low to high agency behavior? If we're relating translation gaps with choice making, how do we look at low and high agency behavior? Well, translation gaps can be very, very large or very, very small, and so you can have higher or lower degrees of complementarity or inconsistency, more important or larger trade-offs. So an example of a very narrow translation gap is solving the equation x squared minus 1 equals 0 for x, versus solving the equation y squared minus 1 equals 0 for y. Here we're swapping the affordances of y for the affordances of x, and really in this specific context I've just outlined, there is very, very little difference. Of course, depends on the context. I know a lot of people who, when handing in their homeworks, if they couldn't write a particularly difficult symbol in one of their proofs, they would swap it for another one and then write at the end, let this symbol equal the easier one that I chose to solve this proof using. So, example of a very wide translation gap is the one I mentioned before between matrices and vectors. We're able to perform operations with these matrices and vectors in the diagrammatic setting much more easily. That's a very, very huge advantage or difference. Something in between, here we have, I guess, a less standard, you might not think it's so much as a translation, but we have translation between a proposition and its statement to a proof of that statement. This is, I guess, for someone who's been through some years of mathematical, like university mathematics, that's a fairly standard translation that you might expect to do. And so this is the statement that, okay, if n is an integer and n is odd, then its square is also odd. And you prove this by noticing that, well, an odd number is one more than an even number, so we express n as 2 times an integer, an even number, plus 1, and for some integer k. And then we square that expression, we get that n squared also is of the form of an even number plus 1, so an odd number. But we don't just recover the statement, we actually also recover some additional information, namely that n squared is not only an odd number, it's also 1 more than a multiple of 4, because we have this extra multiple of 2 lurking around in these brackets in the middle of this proof here. And so, yeah, it's a small difference, but it's, it can make quite a big difference if you cumulatively as you go on through mathematical text. An example of an even wider translation gap is, say, example of the real line or a line versus all the ways you can assign a number to points on that line. So 2 of the largest areas of mathematics are devoted to the different affordances of these objects or presentations, geometry and algebra. And in algebraic geometry, which is another large field of maths, exploiting this difference in affordances is a key component of the vast majority of proofs. So now to put all this into context, I would like to look at the sorting algorithm example that we've seen in the paper by Zhang, Goldstein, and Levin, to see how this choice making and translations are happening in that context. Okay, so here I'm presenting with you some starting array of numbers, list of numbers, whatever you want to call it, with a particular linear ordering, with particular sorting. And then at the first instance of the kind of first step of the algorithm, we might have to choose between, or implementation of the algorithm, we might have to choose between different linear orderings that we then, that this array, different linear orderings on the same list or set. But let's notice something interesting here, that when we're talking about these different choices that are being made, I'm using the definition of agency as choice making between logically inconsistent pieces of mathematics, but here there is actually there's no inherent logical inconsistency. I could just say that each of these linear orderings is just a different set with a different linear ordering. There's no problem there. I see no inconsistency. The inconsistency arises when we identify each of these sets with linear ordering. We say, okay, there is some sameness here, and once there is identity, then two different linear orderings cannot be compatible within the same mathematical object or label. So this is denoted by this kind of assignation of this array to the variable a, say, for example. Okay, so at each stage you make a choice of a different linear ordering or a choice is made. I don't say we make a choice. A choice is made to produce a new linear ordering, again assigned to the same variable. And what we study at the end is not all the possible choices that could be made. It's the path that agency took. It's the final outcome of all the individual choices that were made along the way to reach some goal. And I think that's quite interesting. It's quite an important distinction to make, or observation to make, that we observe and study. For example, the sortedness. We have a number we assign to understand how sorted an array is, and we track that through this path. A particular instance, we might run the algorithm many times and compare the different paths that were made to reach the same goal. But each time, it's a final kind of static thing that we study and draw information from. So my proposal is that agency emerges from translation gaps. So I mean this in two possible ways. One is that agentic behavior is seen when translations are made. Translation gaps give room for agentic behavior to be expressed. And when so in the second possible meaning of this would be that when we look at an agent in a new context, we've made a translation. So behaviors that emerge may do so because of the change in affordances of the relevant presentation systems. So now I would like to extend the sorting algorithms example to more traditional mathematical literature and to see what these paths of agency might look like there. So here we see the difference of two sets. This presentation is being identified with the expression a minus b. We then have another identification with the phrase all the elements of a that are not in b. We again have another identification via this equals sign to this set notation, expression in set notation. And we have another identification to this diagram presenting this presentation of this difference of sets. So this is how we trace identity through mathematical literature. In Marida Altman's framework, it's called a filament because it looks a bit like a thread, a filament through the literature. And this is the place that we will start to look for. This is kind of, I guess, a path that agency took. There were choices that could have been made or to different presentations we could have navigated through in this text, but this is the one that we see at the end. And so, yeah, this links to the definition of agency of achieving the same goal by different means. And so I want to give an explicit example of two different ways where you might see these paths, these filaments through mathematical literature. So coming back to this proof that if n is odd, then n squared is also odd. So first, one of the main observations, the main techniques of this proof is to express n as one more than an even number, but we could have equally expressed it as a general even number plus or minus any odd number. Here I've taken 2k minus 1. Here we're swapping the affordances of the expression 2k plus 1 for the 2k minus 1. It's a narrow gap. It's a small translation. We're making a substitution, but we see that this choice here, or this translation, propagates throughout the proof. We end up at the same statement, the same example of the proof, but the intermediate steps are slightly different. And so, yeah, these are two different ways that agency is exhibited in a very kind of minimal agency setting, or within navigating a very narrow translation gap. So I'm speaking about agency in much more abstract context here. The selection pressure is quite obvious, perhaps. We're constrained to the translations and choices that remain logically consistent with and moving towards the goal of this proof. How might we observe agency as evolving without such pressure? And how might we map out the analogue of our morphospace of possible behaviours in mathematics? So one cannot remove context entirely, but perhaps what we can do instead is better understand the terrain described by the collection of possible translations. So, with this I present our final definition. So traditional abstraction is this kind of reductionism. It's looking at all the things that stay the same, that are common between all physical presentations of this concept or idea. But that's just focusing on some kind of identity part of it. That is not the I'd like to propose a new definition of abstraction as the collection of presentations obtained under translation. So most importantly, that includes both the translational invariants and the translational differences. So bringing together mathematics and biology, making abstraction physical in this way, Rita Altman's interpretive framework moves away from essentializing biology to a more organic mathematics. So this brings us back to our the anecdote at the beginning of this talk, so I want to say that abstraction is the whole physical landscape of presentations, the similarities and differences. And perhaps the name that we give to an abstract object is just a name for the physical body and behaviours that are too vast and distributed for us to recognise by any other means. It doesn't make them any less physical. So I would like to summarise the talk so far, the ideas we've had. I challenge the assumption of this non-physical Platonic space, saying that it was not necessary to implement the main pillars of the research framework that Levin is proposing. I wanted to propose that ingression is translation, that agency is choice-making due to logical consistency, and that logical inconsistency can be generalised as complementarity of translational differences. That filaments in maths literature are paths exhibiting agency, and that abstraction is organic. So to understand how abstract patterns control physical behaviour, we need to look not only at what stays the same, but the subtle but key differences in presentation systems that we create through translations. So mathematics has always been about the art of making translation gaps narrow enough to preserve important structure, but wide enough to be able to move in just the right way. So I would like to use this framework to bring biological theories over to mathematics to understand mathematical practices of translation better, and hopefully focus our research efforts to understand agency. Focus our efforts on these translation gaps and the affordances of the varied substrates that we will encounter in this research programme. Thank you very much for listening to my talk, and I welcome any and all questions.